minus 3. Very, very important. We have to make sure that the limits of my integration match the variable. Very, very important. Ben, do you want to have a go and tell me what the u substitution should be?
Is it x squared minus 3?
Uh-huh. Because the derivative is up here. Almost. Do you want me to do it the long way or the short way?
Let's do the short way.
Short way. Du is 2x dx. I have x dx, so I'm going to have a half. If you prefer, you can write that. Dx is half, no, 1 over, no, I'm just not even going to do that. I'm going to let you just work it out. Dx, I have x dx, I'm going to have half du. So I've got 1/2 the integral of, leave the limits for the moment, this is u, right? So that's u to the negative 1 du. Was that too much in one go?
Maybe.
Okay.
Sorry.
That's all right. This is 1 over u times du dx if you prefer. Actually, let me write it slightly differently. Let me go 2x dx. Now you can see I can replace that with du. So that is 1/2 1 over u du. Now, this integral, I'll wait till you can all watch. Okay. This integral is still dx, so these limits are 2 and 3. But this integral is du, so the limits must be u values. This will actually save you work in the long term. So we're going to go, if x is 2, then u is 4 take 3 is 1. And if x is 3, then u is 9 take 3 is 6. So I'm actually integrating from 1 to 6. Integrating from 2 to 3 with respect to x is the same as integrating from 1 to 6 in u. And if I calculate these, I don't have to substitute u later on. I can just go 1/2. Oh, what's the integral of 1 over u? Nope.
Wait.
We just did it. We just did it.
Log thing?
Log u from 1 to 6. And I don't have to change, yeah, that's nasty. I don't have to change u back into x at all. I just substitute 6 and substitute 1. They're positive. I don't even need the absolute values. They're all positive numbers. Okay, so you can actually just write that. Or if you prefer normal brackets, it doesn't matter. It's all the same because we know we're using positive numbers. So I've got 1/2 log 6 minus 1/2 log 1.
Isn't that just 0?
Correct! Log 1 is 0. So it's 1/2 log 6.
Interesting.
Let me give you one so you can practice. Change of limits. X squared plus 5 dx, oh sorry, to the sixth, why not? Are those numbers going to be too big? No, they'll be right, from 0 to 1. Follow it through carefully. Remember to change the limits when you change the variable. Two x, I need a half. Maybe I'll write it the other way. 2x dx. Did I get my values right? 0 plus 5 and 1 plus 5, yes. The numbers might be disgusting though. U to the 7th on 7, 5 to 6, that's going to be horrible numbers. Six to the 7th on 7. Oh, I take the 7 out, right? And I can't be bothered calculating it.
Yeah, I've left it like that.
Yeah. That's what happens when I make questions up and others get too big. I will tell you one other thing you might, and I'm pretty sure you will see, you might see an integral like this, sine x cos to the 7th x. Maybe we'll do this one so you can see what happens. Can you see something that is related to the derivative of the other?
Cos.
What about cos? They're related by derivatives, right? Take the complicated function, let u equal the inside of this function, which is cos x, because this is then u to the 7th, and its derivative is negative sine x dx. So this one is negative integral of u to the 7th times negative sine x dx. And negative, no, to make sure that's clear, negative sine x dx is du. Which is, come on pen, finish the lesson, negative u to the 8th on 8, which is negative, I'll go 1/8, that was a mess, negative 1/8 cos x plus, sorry, cos to the 8th x plus constant. Very similar to what we've been doing. You're just looking to see if you can find every time this is some multiple of the derivative of that bit. Always look for that pattern. It simplifies a wide range of integrals. A very, very useful technique.